when you charge and when you discharge a battery for economic reasons. Today we'll be talking about the lower level systems that allow you to squeeze as much power and energy out of the cells as possible. Given cells make up a big part of battery BOM costs, even still today, it makes sense that we invest R&D effort into using those cells to their utmost and not leaving any performance on the table. The challenge of BMS often arises when you're dealing with a wide variety of different cell types. Batteries go through all sorts of different conditions. They can be subjected to different temperatures, different usage profiles. The BMS has to deal with all of that. And we've come a long way with battery intelligence over the years. Early BMSs measured current, measured voltage, made some coarse estimation of state of charge, maybe state of health if you're lucky. We've come a long way since then, introducing equivalent circuit models, Kalman filtering, for those that are familiar with that. We've developed thermal models, but one of the common themes of battery management systems to date, and I'm sure there's exceptions out there, but by and large, we've been living in a world where battery management systems, for several reasons, which we'll touch on, abstract from the actual physical state of the cells. They're not modeling the different parts of the cells, the cathode, the electrode, the separator, the electrolyte. We make coarse estimations and generally extrapolate state estimation from that. And the reason I wanted to pull this panel together is these are all professionals that are helping make us pivot from that world to a world where we care more deeply about what's truly going on in the cells, modeling the degradation of different components of the cells and making more physics-informed decisions of the state of the cells. And with that, we expect that we will get more performance. So you'll get more energy. You'll be able to push the cells harder when you're discharging or fast charging. That you'll better be able to detect anomalies, breakdown of certain compounds in the cells, impending failures, ideally before it causes any loss of function. So this is an area of a lot of focus today, and we're going to touch on two key technologies. Physics-informed machine learning is one area. I get a lot of questions being in the BMS space about the role that AI plays in the future of battery intelligence. So we'll talk a bit about that. And the second technology that is nascent at the edge, but has existed for a while in the lab, is EIS, or electrochemical impedance spectroscopy. It's a mouthful, and there's a lot of science behind it. We'll try to make it really approachable. But we'll touch on both of these emerging technologies that I think are going to be causing us to pivot into a world where we truly model the actual physical processes of the cell. What I love about this panel, frankly, is in my role at Tesla, I wasn't the PhD in the room, wasn't coming up with new strategies really for estimating the state of cells. My team would receive these ideas from other folks. And so my perspective here is one of really curiosity. I have a high level understanding of where we're going, and I'm really curious to hear from you guys how we're going to get there. I was going to read all of your descriptions, but I've been talking so much already. Why don't you all just give a bit of an introduction about yourselves, and then we'll get into questions.
Yeah, so my name is Timothy Carlson. I just finished up part of my dissertation at UC Berkeley. I was studying modeling and simulation of solid-state battery materials, particularly the development of the physical models that model the systems. And so we're trying to expand the way in which we can think about these battery systems and the way in which physics are coupled. So we're trying to come up with electromagnetic, chemo, mechanical, thermo continuum models to try and efficiently model all of the physics we can fit into these cells. And then I'm also, currently a consultant going to be moving into a AI scientist role at Dassault Systems. So we make SolidWorks, if you're familiar with it, but also Abacus, continuum physics modeling software, and Materials Studio, trying to predict battery health and such.
There's one line from your bio I really want to read here because it's great. Timothy's research focuses on both the development of theoretical and computational multi-physics models for solid-state energy storage materials and exploration of AI surrogate accelerated homogenization strategies for a high-fidelity analysis of complex solid-state battery systems. I practiced this in the mirror before I came, and I just wanted to say that out loud. We'll get to you defining that, because I think there's a lot to unpack there.
I'm Evan Murphy. I'm the head of technology for Zitara and Elysia for battery energy storage systems. My background is in software. I'm originally just a generalist software engineer from industrial software, and I moved into data for battery problems 7 years ago when I co-founded Zitara. We work with real systems, now exclusively grid scale systems, to get the underlying data that drives the behavior of these battery systems, interpret it in the most useful way using models, using machine learning, to allow operators of grid scale storage systems to make intelligent decisions about how to use, how to dispatch, and how to maintain and build out their systems.
Hi, everyone. My name is Omer Tanović. I lead a BMS algorithms team at Analog Devices. My background is in control theory and electrical engineering, signal processing. I spent about 2 decades developing algorithmic systems, mostly in oil and gas, communications, and the past 7 years in the battery space. So I've been with ADI 7 years with Analog, and during that time I was in the CTO office and kind of worked as an entrepreneur within a big corporation. Led development of the EIS-based battery insights technology, and kind of moved into the product line to start the product line based off of that to kind of build software applications, software products that complement ADI's BMS ICs as well as kind of BMS system level solutions.
All right, hey everybody, my name's Kevin Hayes. I'm the co-founder of a company called Morelle. We focus on 15-minute fast charge battery solutions, mostly for fleet applications. Actually, I'm originally a chemist by training. Spent some time surfing around the National Lab System. Spent some time making some high silicon-based cells for eVTOLs and electric vehicles. Learned a lot in this space and learned that fast charging, it's important, 0 to 100% in 15 minutes. We can do this today, but it really requires controlling the batteries efficiently. And understanding on how these batteries age, and that's what I really care about here today.
And you have your ultra fast charging e-bike in production now, hey?
That's right. Yeah, we're actually demonstrating this in an e-bike. We're introducing the first 15-minute fast charge e-bike to the market this year, really to just show people that fast charge is here today. It can be done if you do it correctly.
Awesome. So we've got a great panel, folks in research, hardware, OEM and research at the end. So let's dive into it. Physics-informed machine learning. I'd love to split this topic into 2 sections. How we have been using it in development, where we want to see it ultimately in production. Starting maybe in development, how do you guys see modeling and simulation used in cell development today? Maybe Kevin, you could start.
Yeah, I think more and more we're moving to a phase where modeling is increasingly important due to the time frames to do any sort of cell development. If you look at the old school way of doing this, you make your material, you put it in a coin cell, and you test it, and you test it, and you test it, and hopefully you're testing it a year later, you know it's good. If it's really good, you're testing it 2 years later, and but more likely or not, you're testing it for a couple weeks, and you know it's time to move on to the next one.
Perfect, thank you. Anybody else want to chime in on that?
I mean, yeah. So modeling and simulation has been used in a number of different industries. And I mean, since the 70s in the structural sort of mechanical industry, and more recently with batteries. The problem has been that until maybe 20 years ago, battery models were very, very unsophisticated and had very limited prediction capabilities. But in the past 5 years or so, my company, Dassault, and a number of others have vastly improved their battery simulation capabilities. And so now it can serve, at least for some chemistries, as like a full digital twin of a battery cell and can predict battery cell behavior prior to implementation. So that way new chemistries can be explored quicker and new designs, new microstructure orientation. So it's a very useful tool in design and can really accelerate processes.
You had this killer phrase in your bio, AI surrogate accelerated homogenization strategies. Can you define that for us?
Yeah, okay. So basically these battery cell materials, especially in what's used today, are inherently multi-scale, multi-physics. And so multi-scale being you have a matrix of particles embedded into an electrolyte, which computationally is difficult to model. Obviously at the atomic scale, impossible with current simulation capability. And even still, to fully resolve one of these microstructures in a full cell, let alone full pack, would create a number of degrees of freedom in your model that would take probably more than the current human lifespan to simulate. And so the idea behind this AI accelerated surrogate modeling is to, or homogenization is to have a sort of two scale model that can simulate the microscale via some simplified geometric models instantaneously after training, that then upscales into a full-scale continuum model that runs no slower than the current sort of state-of-the-art continuum models, but with a much, much higher degree of fidelity because it's using like real microstructures, just accelerated using AI. And then like the pinnacle of this would be to use sort of AI acceleration at both scales. So you're accelerating the small scale and macro scale simultaneously using surrogates, which are just trained physics models that can predict instantaneously based on like high fidelity physics.
Moving from the lab and from development into the field, we're on the cusp of bringing a lot of that to real-time operation and use of cells, operating these at the edge. Before we dive into why that's happening, what that looks like, I'd love to hear really from any of you on what this could unlock in the field, in the cells. What's the promise of this?
We know that different cells in the field are going to behave differently. The best cell in a vehicle and the worst cell in a vehicle will have different lives, they'll have different performance characteristics. That doesn't have to be a total mystery. With better modeling, we'll start to learn, why do cells do what they do? How can we manage through the fact that these cells have various lives? And as much as the models that are on BMS today have improved that a lot and have room for improvement, continuing to do these higher power models and like have kind of a chain of engineering from the supercomputer models all the way down to real-time BMS models is really valuable to being able to enable things like extreme fast charging, long lifetime cells, and management of power and energy.
Yeah, I think when you talk about the performance of the cell too, I mean, you have the cell performance, the chemistry, everything. But then when you're operating the cell, you're actually limiting that performance quite a bit in some stakes in order to do it safely. So I think we're now at a phase at pushing that window as far as possible to what you can actually do with the chemistry and not just what you have to limit the cell to in order to do so.
Just a quick comment. I mean, traditionally, the OEMs, and they still do that, they use equivalent circuit models, right? So the models that are actually embedded in these systems, right? Whether that's vehicles, ESS, robots, drones, eVTOLs, whatever they are, most of the time it's equivalent circuit models. And basically you're limited to your empirical model and your voltage and current measurements and kind of voltage outputs that you get out of such a system. With these physics-inspired AI models or physics-based models in general, you get insight, visibility into the states within the battery, which kind of unlocks, a world of opportunity, in terms of safety and kind of pushing the performance bounds of your batteries and the system as a whole. Right?
Maybe worth noting too that like a big reason that these sort of physics-based models haven't been used is because up until very, very recently, it would be totally unfeasible to run one of these models both quickly and on the compute available. But with cloud and just the acceleration that a trained surrogate can bring, it becomes possible now.
One interesting thing about that is the availability of compute and the size and scale of batteries are both changing really, really rapidly. So one thing we think about a lot is basically gigawatt hours divided by gigahertz. Like how much compute do you have on site somewhere? How big is your battery? Like on one end, you've got a cell phone, relatively small battery, really powerful processor. On the other end of the spectrum, which is where we are, you have hundreds of megawatt hours or gigawatt hours of storage and stationary storage. And if you're lucky, you might have one underpowered industrial computer. And so every spot in the middle in that continuum is occupied, and you need to know where you're going to be working so you know what flavor of model and what flavor of capability is appropriate for your system.
We have been seeing a shrinking of the gap in memory cost and the amount of memory that exists in edge devices.
Until
and
recently.
Until recently.
The last 6 months, anyone else here being affected by the RAM apocalypse?
RAM is expensive.
I missed the memo on that.
Oh yeah. The AI people are taking all the air out of the room if you're in VC and all the RAM out of the room if you're operating computers.
That's perfect. I mean, that segues into the next question. We've been seeing gains there. There's more opportunity at the edge than there has been, but we still care about efficiency at the edge. I know, Tim, you've done some work on reducing the order, reducing the complexity of these models. Could you talk a little bit about that process, what that involves, and what the trade-offs are there?
Yeah, I mean, so I think that a lot of the older models and the ones that have been used reduce the complexity to the point where you lose critical physical insights. And so now the sort of battery analysis community is at a point where, starting from these well-developed physics models, we're trying to sort of reduce the scale again, but in a more maybe intelligent or predictive way, physics-informed way. So we're homogenizing the physics itself rather than the system, which is one way. This is just model order reduction. This is purely like analytical in a perspective. Another way of reducing complexity is by sort of pre-computing outcomes and then fitting. This is surrogate modeling. It's more machine learning than AI, but now everything's AI. So we're running a lot of simulations using these high fidelity models and then predicting outcomes from these simulations. And what you can do with that is, given a set of inputs and a known battery, it's like if you can measure the state in situ, then you can predict its state in the future, like plated lithium, degradation, damage, et cetera, just by a current state. And it's like a reduced order model, just in the sense that the complexity is pre-computed rather than computed during the process, which is like sort of where the future of modeling is going.
Just to add to that, when it comes to kind of computing and how much power you have, so what's happening is in the BMS, right, whether that's in the vehicle, right, in automotive industry or ESS, kind of the processing architectures are distributed or hierarchical, maybe not distributed, hierarchical, right? So in the vehicle, you have a edge of the edge BMS, which is usually very, very constrained, and you got to run your safety loops over there. You can't move that to, say, to the next level, maybe in a zonal architecture where you have a zonal controller, and then you have maybe a high performance compute where you do your ADAS and kind of vision and all the, say, self-driving algorithms, right, run at that level. So as you kind of move up and down, there are things which have to live at the very edge of the edge. So while you can offload some of the compute up, you still have to do some of the most important stuff, most critical stuff at the very edge of the edge. So no matter what, you can never just live with big complex models. You got to reduce them to a certain order, and then it becomes a game, right? A trade-off, or what do you do where, and how much of it you offload, how much of it you move up and down, and that's where the secret sauce is in most of the cases. And it's similar to ESS, right? Whether you operate at the rack level, or you operate at the container level, or kind of very BMS, which is, say, at one of the smaller packs that the racks are built out of.
At Tesla, we would often receive new cells using pre-existing algorithms and have to ensure those algorithms worked well with the new cells. And we got really good at estimating how long it would take to introduce a new type of cell, what the test suite would look like. As we move into a world where what's happening at the edge is more complex, more sophisticated, maybe there is a certain aspect of non-determinism there as we introduce AI. How do you envision training and then validating something that is much more complex at the edge? What would that look like for teams that have to make it work?
I mean, I think here we talk a lot about the physics-based approach of knowing everything internally about the system. But there's also the other side of this, which is if you can just throw a whole load of data at the system and you don't care what happens in the black box, and you can say, okay, just take all that data and then tell us what we need to know on the other side of it. I think that's another area where training your AI algorithm appropriately could really get you there.
I'm fairly negative on doing a pure black box approach to this because it's so easy to trick yourself. If you can take any model you want, and if you start with the appropriate input data, you can get any quality of result you want. Like, people ask us all the time, what's the quality of result? What's the fidelity of our algorithms? And the answer is really, well, on what kind of data set and on what kind of application. And so understanding the diversity of your application, understanding the data that you're going to be able to put into your system, and then understanding a little what's going on inside that black box to make sure you're not tricking yourself on its behavior. And that comes to validation, to exactly your point. And I think for all the modeling we can do, for all of the amazing supercomputer high-performance modeling we can do, we have to get back to ground truth. We have to get back to real physical systems. And we have to look for opportunities either in field data or in the lab to say, here's what this system really did. Here's how well our model performed. And here's how this would apply in the real world if we aren't already in the real world using field data.
Yeah, it's a good point. Like, these surrogates don't just exist in a vacuum. They're trained on real physics, but when the physics expands, they just fundamentally need to be retrained and revalidated. And so whenever something new is introduced, it introduces a new process. And while it can be used in practice once it's trained, it's a non-trivial effort to train these models with new physics, and it's even non-trivial to introduce the new physics into the model at all. It requires a lot of development to both validate the physics and then validate the model. It's every time something new is introduced, it needs to be revalidated.
What would that validation look like? Like, it's one thing for us to speak to it. What does that mean in practice?
Correlation to experiment. Once you have, does the theory predict the experiment, and then is the experiment predicted by the theory?
So just cycle testing across a wide variety of conditions?
Basically. You can transition into the EIS topic from this too.
We'll get there.
Maybe to add one more dimension to all of this, right? So let's say even if your use case would allow to train that and validate that model, even if you actually could do that, given all the data that you're going to collect, in many instances there's regulatory limits on what you can actually run in terms of the software and the algorithms that are there, right? So for example, in aviation, in eVTOL, you cannot actually run something that kind of changes, almost randomly. There's safety limitations and kind of regulatory limits on what kind of software can run. So you can't actually have an ML model which kind of updates itself, on the fly, beyond some safety loop. And there's kind of similar regulations in automotive, not as strict, but still kind of that validation step now becomes a big hurdle for OEM to implement such algorithms. So there's some of the regulation that will have to change, and I'm sure it will under the pressure from the industry, right? If there are solutions that actually bring value to the end customer.
It sounds like an implementation that would be acceptable today would be something that implements AI, but with firm guardrails around it to prevent unintended loss of propulsion, for instance.
Yeah.
Okay. Let's pivot to Tim's point to electrochemical impedance spectroscopy, often referred to as EIS. I'm sure many people here are familiar with it, but I'd love to start with an overview of what it is, just fundamentally. I keep looking at Kevin because he and I have had several conversations over beers about EIS.
Okay, so it's my job to teach you guys about EIS.
Give her.
No, most simply speaking, you're applying an AC signal to your system. You're perturbating your system, and it allows you to look at how far your frequency is moving out of phase and how far your frequency peak is shifting, basically. All that said, if you sweep it over a long amount of frequencies, you can learn a lot about what's going on inside the chemistry. But what's really important to remember about EIS is it requires stability, linearity, and continuity, which means generally it can be pretty slow and you have to repeat the measurement a bunch of times to get a good measurement.
Now, it's been used a lot in the lab where you can control the state of the cells. Anybody feel up to speaking to how they've used or how they've seen it used in cell development or cell testing?
I mean, most strictly speaking, generally, you will be running EIS, what we call a spectrum or a Nyquist plot across. You get a bunch of humps, lumps, and lines. Frankly speaking, you can take those, you can model them against an equivalent circuit. If you do that modeling correctly, you can know a whole lot about the chemistry of your system. If you do that modeling incorrectly, then you can know nothing.
I guess just for an example, this is one of the primary ways in which conductivity of an electrolyte is measured, because it's very difficult to actually take measurements on an electrolyte, just in general.
Yeah, 100%. I mean, a really great use of EIS in the laboratory is fundamentally understanding how your cell ages. You can really dive deeply into SCI growth, into changes in the resistance in the cell, changes in how diffusion's taking place within the solid, within the electrolyte, even how non-active components are participating in it. It's actually a very strong technique to get a ton of information out of. Again, the biggest challenge always comes into, it really involves the input and how you're modeling it. And I've seen really good modeling and I've seen really, really poor modeling. And you can get any answer you want out of an EIS spectrum if you look for it.
Omer, one thing I wanted to ask you about EIS. I know ADI has chips on the market that do this. What I guess developments have unlocked this capability in recent years?
So to kind of piggyback on what Kevin and Tim have just said, right? I mean, EIS has been used in the lab, right? And the reason it hasn't been used outside of the lab is not that there is a limit on the physics. Physics is not limited. It's just that the real world does not look anything like the lab, right? So the real system, the battery system in the vehicle, and I'm going to use vehicle as an example, right? It generalizes easily to other use cases. Battery system in a vehicle is super noisy. It's dynamic, right? EIS in the lab is taken under, usually, right, 99% of the cases, under assumptions that, you know, the battery is in a steady, relaxed state, and you can take a trustworthy signal measurement out of that battery. In the real system, it's nothing like that. So really what, you know, we at ADI, and I'm going to say, you know, where we think we've differentiated with the solution that, you know, is coming out to the market is that we look at that not just as another measurement, right? We're a company that has been building ICs for 60 years, right? We're building BMS ICs for more than a decade, all right? And classical VIT, right? Voltage, current, temperature. But we don't look at EIS at impedance as just another voltage measurement, just another current measurement. We look at it as a fully integrated solution. So basically starting from the silicon, from the BMIC, right, to the system integrated kind of signal processing engineering chain, all the way to the software, that this system together gives us an ability to translate that embedded measurement that you get, that raw data, translate into an impedance measurement that actually traces back to what you would get in a lab setting. So and we believe that EIS is the future of next generation of BMS because it really gives us, as Tim and Kevin have mentioned, really gives us a window, a very big window into what is going on within the battery.
I share your optimism. Like, I see a lot of reasons to be excited about this. Also hearing from both of you guys how you need to have a good understanding of the state and control the state of the battery when you run this test. If I was a BMS development engineer and I wanted to integrate this into future BMS designs for whatever my product is, can you give us broad strokes of what that development program would look like? Because it isn't just another voltage sensor. It's sophisticated, it's complex. There's a lot to consider. You don't just want to start consuming data from this chip if you don't really know what you're doing. So what is that path? What does that roadmap look like?
Yeah, so there's multiple aspects there, right? One is you need to understand. So battery doesn't have to be, super relaxed and easily perturbed during the EIS measurement, but it doesn't require that. EIS does not require that. But what it requires is a well understood system that the EIS is operating in and visibility within that system. So that's what you need to ensure. So what does that mean in practically? Well, you need to be aware of the operating conditions of your battery that you're taking the EIS of, right? You need to understand the temperature, state of charge, and kind of other system level impacts. The second is you need to have a measurement which reflects the battery and not just some random kind of system effects. That's extremely, extremely important.
Does that speak to the electrical design of the circuit board and the interconnects to the cells?
Exactly. And then, the excitation current, how are you, if it's, say, current excited EIS, right? How do you build that excitation current circuit? What kind of excitation do you use? Your frequency ranges and so on and so forth. A lot of kind of engineering choices. And another one is you need to build it in such a way that your measurements are a trustworthy and repeatable. And then, because if you do that, then over time, you can actually correlate your measurements with the changes within your system. And you can trust that you're capturing the effects and not just some kind of random changes because you can't get repeatable measurements. So that's kind of on the hardware side, right? But then you also have to look at it from the inside side, right? What are you going to use that EIS for, right? So you need to if you're, say, developing, some battery insights application software based on EIS, right? You need to do a lot of experimentation, correlate that EIS with the insights that you're looking for, figure out, they'll understand what good means, what bad means, and then with that, combine that with the design of your system, BMS system, right, and everything around it, to be able to get such measurements, throughout the life of the vehicle.
Right. So clearly not a drop-in replacement. You need to consider it from the earliest days of new battery and new electronics design.
Yep. Absolutely not, because there's no free lunch, right?
Right.
So you get a lot out of it, but you got to pay in some sense.
It's like X-ray vision, Superman's X-ray vision, but if you don't do it right, you've got like Coke bottle glasses on. I don't know, maybe that was horrible.
Did you want to add anything, Evan?
Just the power that you get from EIS is fundamentally about understanding the physics of the battery better. And that's going to open up this model, or this ability to model a cell that's much more complex and also much more possible, exactly like we talked about earlier with in the lab. building a model that doesn't actually represent reality. And so one way or another, you are doing feature selection or order reduction. You're looking for specific behaviors that you can reliably draw from that signal. And you need to have a plan for what does it look like to start with that deeply physics-informed, physics-based model and move down to similar but much simpler, robust features that the BMS can use on the fly. And that's a whole separate kind of characterization and modeling than the cell characterization that people are doing today with EIS. There's an entire new kind of EIS characterization work to do when we start talking about getting it in the loop on a device.
Perfect. That makes a lot of sense. Thank you. I think we're out of time. Yeah, we're almost out of time. We have time for one question. If anybody has a question burning a hole in their mind. Yeah, in the back. You're referring to things that happen outside the cell and where else you might be measuring voltage in the battery?
I mean, this is not the fun new research, but most problems in energy storage are balance of system problems. They're water ingress, they're unexplained self-discharge, they're overheating due to external, like insulation and external heating. And that's super important for delivering battery systems that meet their requirements. There's a ton of work to do there. It's maybe a little afield of new developments in batteries, but if you don't take that into account, your model, your machine learning or your other system model is going to give you information that doesn't reflect reality because it's not getting the inputs from reality. So there's a lot of important work to do there.
So, and to add to that, and maybe address the question directly, right? So what you can't measure, you can see, right? At least if you cannot at least implicitly measure that, right? Maybe not explicitly. So what we've been working on is a use of EIS for temperature estimation. And there's reasons why OEMs kind of want that. I'm not going to get into that, but just for that particular one, right? Say there's a corrosion happening somewhere outside of the battery, but within the battery pack, right? If you have, say, good, accurate cell temperature estimation, but you see something unexpected happening, say there's some corrosion, there's some resistance increase somewhere kind of along the chain, and there's some heating being generated there, which is kind of transferring back to the cells, which are in the vicinity of that mechanical issue that you have. That can trigger you that there's something wrong happening, right? So you might not be able to classify it exactly what's going on, but you can actually flag it as there's something wrong. Go to the body shop and check it out.
Oh yeah, nothing about what we've been talking about today obviates the need for measuring the potential between high voltage, positive, negative, and chassis. That's very much a part of all the BMSs that we're imagining here. But this would be higher level algorithm stuff. Well, thanks everyone. Appreciate the time.